And the next speaker will be Yagub Aliyev. And I
Yes,
think if the speaker is ready, maybe we can start.
Yes, I'm ready.
Okay, so then let me introduce Yagub Aliyev from the ADA University Baku with the talk Geometric Properties of Interception Curves. So please.
Let me first check if everything is visible.
It is. Yes.
You can hear me perfectly. Okay, then I can start. I represent ADA University from Baku, Azerbaijan. So my talk is rather simple, very simple. I consider this question. Suppose that 2 points, P and Q, initially at O, 0, 0, and A, 1, 0, respectively, move with constant and equal velocities so that Q is always on the line x equals 1 and P is on the ray OQ. Both curve is defined by the point P. This problem appears in many problems, in many references, but it also appears in problems related to interception of high-speed targets by beam rider missiles. These are the two references about this application. So I can try to explain this also on a picture. Let me move this to, okay. So on picture, this means that P moves along this blue curve. And with the same velocity, Q moves along this line x equals 1, so that O, P, Q are always on one straight line. What is the formula for this curve, or how can one define this curve? If we will use the well-known formula for the length of curve given in polar coordinates, then we obtain this equation for this curve. It is an integral equation, of course, but it can easily transform it into an ordinary differential equation by taking derivatives of both sides. We obtain this non-linear differential equation with initial condition R0 equals 0. This equation is not easy to solve. In the encyclopedic book by Kamke, Differential Equations and their solution methods, I think this book is also available in English. Some methods were described to solve the previous equation in polar coordinates. This equation can also be written in Cartesian coordinates like this. Again, by taking derivative, we obtain, again, nonlinear differential equation. In the Kamke's book, there are some methods which one can try to solve these problems. I tried one of those methods and I obtained this parametric representation. As you can see, the solution is written here through some integrals. In this case, these are elliptical integrals. Using this parameterization, one can draw the graph of this function, for example, using Maple and other mathematical software. There are other parameterizations of this curve, but this one is the most useful one. One can use this to prove some theorems about this curve, to study some geometric properties of this curve. Let us start with simple geometric properties. I will need to return to the picture again to be able to explain this formula. So these are simple geometric properties. First property says that if this tangent line of the curve at the point P intersects the y-axis, x-axis, and the line x equals 1 at the points U, F, and T, then this equality holds true. UP equals OU plus TQ. UP equals OU plus TQ. Not difficult to prove this. Similarly, one can easily prove that 1 minus x, where x is the first coordinate of the point P, 1 minus x multiplied by UP equals TQ. Let us look at the picture again. 1 minus x multiplied by UP equals TQ. X multiplied by PT equals TQ. X multiplied by PT equals TQ. TQ, yes, again. And the last one is another peculiar identity. Sine of angle QPT equals OP multiplied by sine squared of TQP. This angle, QPT, this sine of this angle is equal to OP multiplied by OP multiplied by sine of TQP. Okay, these are not difficult to prove. There are also more difficult properties of this curve, which reveal the relationship between this curve and Leibniz-Cut functions and Leibniz-Cut constants. So the limit of the side PQ, we can look at the picture again, limit of this side of the triangle PQT, when P goes to infinity, when x approaches to 1, so the limit of this PQ is equal to B squared. B is famous second Leibniz-Cut constant. It is also related to Gauss's constant G. And this equality shows that there is a surprising relationship between this curve and Leibniz-Cut functions. It is possible to prove using the same methods that limit of the difference of the other two sides, PT and TQ, approaches to the same limit. Okay, here it is. It would be interesting to compare this curve, which I call interception curve because of the applications in that I mentioned earlier. To compare it with other curves, for example, one can compare it with well-known pursuit curve introduced by Bouguer in 1732. In Bougier's pursuit curve, it is required that the tangent line of the curve always passes through the point Q. So here the rows of T and Q change. So in Bougier's pursuit curve, the direction of the movement of the P is always towards Q, and P and Q moved with the same speed. Q moves along the line x equals 1, and with the same speed, P moves along the curve, so that the tangent line of the curve at P passes through Q. This is a well-known pursuit curve, and it is differential equation is a second-order differential equation with initial conditions indicated here. It is easily solvable differential equation, not difficult, explicit function. And one can find formula for PQ here. And the limit of PQ when x approaches 1 is 1/2, 0.5, which is greater than that B squared that we mentioned here, second Leibniz-Cut constant squared. This means that if one follows interception curve, this blue curve, then one can make the distance PQ smaller than if one follows the strategy of the pursuit curve. This is one interesting comparison of the curve under study with the classical pursuit curve. Here you see the picture comparing these two curves. So here O, P, and Q are always on one line, and PQ move with the same speed. Here, P, if you draw a tangent line through P, it passes through Q, and PQ again moved with the same speed. Okay. Now let us try to solve a similar problem in 3 dimensions. Suppose that 2 points P and Q initially at 0, 0, 1 and 1, 0, 0 respectively move with constant and equal velocity so that Q is on the great circle z equals 0, x squared plus y squared equals 1, which is equator of the sphere x squared plus y squared plus z squared equals 1 with center 0, 0, 0. And P is on the great circle through BQ on the sphere. What curve is defined by this point? Before checking the answer, let us look at the picture to better understand. So point Q moves along this equator, and with the same speed, point P moves along such a curve that B, P, Q are always on one meridian. What curve is defined by these conditions? And the formula for this curve, if we will use spherical coordinates, is very simple. This is actually a well-known function. It is Gudermanian function. It appears in Mercator projection as y-coordinate of Mercator projection. We will see in the coming slides that this relation to Mercator projection is not a coincidence. And Mercator projection is indeed very related to this question. Okay, this was the question and it is answer. Again, this curve has some geometric properties. The first one is very simple. The limit of the distance between P and Q goes to 0. Its proof is very simple, so I included it here. One can easily check that as theta goes to infinity, which means that as this curve rotates around z-axis like this, the distance between P and Q approaches to 0. Not difficult to see from this function. But this curve also has other interesting properties. I want to show these properties to you. First property says that the length of the sum of the lengths of the arcs PT and TQ is not dependent on theta, the sum of the lengths. And this sum is equal to pi over 2. Here T is the intersection of the great circle tangent to the curve at the P with the equator. Okay, we can look at the picture again, maybe. So this blue great circle is tangent to the curve at the point P, and it intersects the equator at T. Then the first property says that PT plus TQ as arcs is constant. It is always equal to pi over 2. Next property is a related property. It says that as theta increases, TQ increases, PT decreases, and both approach to the same limit pi over 4. PT decreases, but TQ increases, and they both approach to the same limit pi over 4. And according to the first property, their sum should be constant. The next property says that spherical angle QPT is equal to BP. QPT is this spherical angle on the sphere. It is equal to arc BP. And the next one is also related. Spherical angle BPT is equal to PQ plus P over 2. BPT is equal to PQ plus pi over 2. These properties can be proved directly, but there is also an alternative approach that I will mention at the end. There is also another property. If a small circle of the unit circle sphere passes through point B and is tangent to the curve 6 at point P, then its spherical radius satisfies this interesting relationship. Tangent squared r is equal to 1/4 of seconds to the 4th half of BP. I didn't show this circle in this picture to avoid confusion. So this sphere, this circle passes through point B and is tangent to the curve 6 at the point P. So it is something like this. A circle on the sphere passes through B and tangent to the curve at P. And it is radius enjoys this interesting formula. Back to the mentioned relation to Mercator projection. This curve, which is shown here in blue dotted line, if it is combined also with well-known spherical spiral, sometimes it is called loxodrome or even rump line, well-known curves in sea navigation. If these two curves were projected using Mercator projection and stereographic projection, then we obtain 4 more curves, which are shown here: orange, green, black, and purple. This yellow one is the asymptote of this black curve. And some of these curves are familiar curves. I put them all in this table. So this phi is our interception curve. That red one is spherical spiral. On the Mercator projection, we obtain this function y equals ln cotangent hyperbolic x over 2, which is, by the way, inverse of itself, and y equals x, which is helix, which are here. Helix is orange, y equals cotangent hyperbolic x over 2 is this green one. On the stereographic projection, we obtain r equals cotangent hyperbolic theta over 2 in polar coordinates. It is in black. And well-known logarithmic spiral r equals e to the theta, which is in purple. These two curves. So the curve under study is related to other well-known curves under Mercator and stereographic projections. Now, these results can also be proved in a different way, in elementary way. One can use this lemma, for example, first lemma, which says that if you have this great circle, equator, and 2 meridians passing through North Pole B, and if another great circle passes through P1 and P2 and intersects the equator at T, then and one more condition, that P1 P2 is equal to Q1 Q2, P1 P2 is equal to Q1 Q2, then surprising result in spherical geometry. I didn't see this result in any book about spherical geometry. Surprising result is that P1T plus TQ2 and P2 plus TQ1 are both equal to pi over 2. P1T plus TQ2 and P2T plus TQ1 are both equals to pi over 2. Similarly, about the circle passing through B, P1, P2, we can write this formula. Tangent squared r of that green circle is equal to this, which is expressed through 4th powers of seconds of half of P1, P2, BP1, and BP2. Using these two lemma, one can prove the previous theorem easily. One can interpret this theorem as a limiting case of this theorem. One can also try to prove the geometric properties in the planar case using these elementary methods, but this lemma are too simple. So if P1, P2 is equal to Q1, Q2, then one can, for these parallel lines, then one can say that OU plus TQ2 equals UP1, similarly this. And there are other relationships which can be used to prove those properties for planar curve easily. The problem that I mentioned was also mentioned in other books. I can mention the paper of Wilder in American Mathematical Monthly from 1931. I can also mention the paper of Zbornik from 1957. I can mention Bailey's paper in Mathematics Magazine from 1994. About the lemniscate constants that I mentioned, you can read from the paper of Todd from 1975. These are all my slides. Thank you for listening.